Welcome, everyone. For today's prep, we're going to start looking at a new differentiation technique called implicit differentiation. And this is not a technique we're going to be using all the time, but it can help us when we want to calculate the derivative of something called an implicitly defined function. So we're going to start by looking at, well, what is an implicitly defined function? And then once we're able to calculate the derivative, then we're going to be able to play all the same games that we've been playing with derivatives, the major one being finding the slope of the tangent line. All right, so first of all, let's look at an implicitly defined function. What do we mean by this? So we're going to be looking at equations involving two variables, normally x and y, but it doesn't have to be x and y. And when we have an equation involving x and y, there's two ways we can define y as a function of x. So there's two ways this equation can be used to define y as a function x. Explicitly or implicitly. We're used to the explicit version. So let's start with that, and then we'll look at the implicit version. All right, so let's look at an example. And this is an example of an explicit function where y is explicitly written as a function of x. So we have a two-variable equation, x's and y's in this equation. So here's an example, y equal to x squared minus 1. So there's both x's and y's, but y is explicitly written as a function of x. So what we mean by that is literally we have the form y is equal to this. So that's what we mean. It's in the form y is equal to. And only x terms appear on the other side. So the only y that shows up is on that left side, and this equation is telling us what y is equal to. All the x's are over here. So this is all the functions that we've looked at in the course so far have been of this form. And, when we graph it, we get a graph of a function. And when we have an explicitly defined, when we have an equation that explicitly defines a function y in terms of x, this passes the vertical line test. So any vertical line we draw intersects our curve at most once. All right, so what is an implicitly defined function? Well, again, we're focusing on our variable y. We have a two-variable equation. So here's an example, x squared plus y squared equal to 4. And this is an example where we can view y implicitly as a function of x. So we can still view this function, or we can still view this equation as defining y as a function of x, but when we read this equation, it's not in that form y equal to. So when we look at this, the x's and y's are kind of mixed together. So it's literally not written. It's not written as y equal to some stuff. We have x squared plus y squared equal to 4. But we could still view y as a function of x. So we have this equation. It gives us a relationship between x and y, but it doesn't tell us what the formula is. So it's implicit. It's kind of hidden inside this equation, what the formula is. Now, sometimes we can actually solve this. Sometimes we can't. So in this case, we could solve this. We could try to solve this equation for y. And when we do, we get plus or minus the square root of 4 minus x squared. And the positive square root would give us the top half of the curve. And the negative square root would give us the bottom half of the curve. So when we deal with equations like this, they don't necessarily have to pass the vertical line test. So the way kind of around that is we focus on a specific point, and then we can look at a section of the curve kind of around that point. So in this case, if we were interested in, say, this point P on the top half of our circle, well, we could use that section of our curve, and that is a function. Or if we were interested in, say, this point down here, well, then we could use the bottom half of the curve, bottom half here, and that, again, is a function. So when we have an equation like this, and it's not in the form y equals, sometimes we can solve it for y, sometimes we can't. But as we're going to see, we can still calculate the derivative, dy dx, without even solving this for y. So this technique is called implicit differentiation. So how is this going to work? Well, when we have our equation, step 1, we're going to apply the derivative to both sides of our equation. Step 2, we're going to differentiate each term, and we're going to end up with a y prime, or maybe multiple y primes, depending on our equation. And we're going to see this in why we end up with a y prime in a second. And then once we finish differentiating, then our goal is to solve for y prime. So we're going to move all the terms containing y prime to the left side of our equation. We'll be able to factor and then solve. So I think we'll come back and talk about this when we do an example. I think it'll be easier to discuss. But while we're differentiating, if we have a term that has only x's in it, we're going to be treating our x just like a regular variable. So in our equation, if we have only an x, well, x is only a variable, so when we go to differentiate, we're going to differentiate it just like usual. If we have a y term in our equation, this is where it kind of gets a little different. If we have only a y term in our equation, well, we're going to do this kind of two-step process. We're going to differentiate it like usual, but then we're going to multiply the result by y prime. And the reason for this is because we're kind of treating y as two things. We're treating y first as a variable, because it's just a variable in our equation, but we're also treating y as a function of x. And we have chain rule that says when we differentiate, when we go to differentiate a composite function, we do the derivative of the outer function, and we keep the inner function exactly the same, and then we multiply by the derivative of the inner function. So this y prime that we're going to multiply by is going to be kind of like this derivative of the inner function. All right, so right now it's all kind of conceptual. Let's get grounded here and try an example to see what we're talking about. So we got this equation, x squared plus y squared equal to 4, and we're going to use our implicit differentiation technique to differentiate this thing. All right, so we want to figure out dy dx. And we're not going to solve this equation for y. We're just going to do implicit differentiation to get our derivative. So let's see how the process works. So let's write down our equation. X squared plus y squared equal to 4. And the first step for implicit is to apply the derivative to both sides of our equation. So step 1, we apply the derivative, kind of just go by term here. So we apply the derivative to the first term, the second term, and then the other side there. All right, so now we differentiate. So in this first one, there's only x's. So this is an x-only term. So when we have an only x term, we're just going to differentiate it like usual, and that's it. So we're just treating x just like a regular variable. Nothing too special here. So we can do our power rule. So derivative of x squared is 2x. Now when we differentiate the y squared, we do two things, because this has a y term. This is a y term here. So when we differentiate a y term, we're going to start by differentiating like usual, but then we're going to multiply the result by y prime. And that's really because of chain rule. So let's see. So when we differentiate this y squared, we do our power rule. We get 2y. And then we're going to multiply the result by y prime. So again, we're viewing y as two things. We're viewing y as just a regular variable here, which it is. We got this equation, just a regular variable in that equation. But we're also viewing y as a function of x. So when we view y as a function of x, we're really thinking of it as there's like hidden x terms. There's x terms that are hidden inside that y. So there might be just a few. There might be a whole bunch of x terms hidden inside that y. So when we differentiate this, the outer function is this power function. So we do our regular power rule. We keep the inner function exactly the same, but then we multiply by the derivative of our inner function. So this is kind of like a chain rule that we're doing. And again, we're thinking of y as an implicit function of x. So we're thinking of it as there's x terms that are kind of hidden inside of the y. All right, so for an x-only term, we differentiate it just like regular. For a y-only term, we differentiate it like regular, but then we multiply the result by y prime. And then for a constant, derivative of a constant is still going to be 0. All right, so this is the first and second step of our implicit differentiation. Now, we want to start to work on solving for y prime. So we want to figure out what y prime is. So when we do this, you want to kind of scan through your equation and look for every term that has a y prime in it. So 2x, no y prime. 2y times y prime, yep, there's a y prime there. And then we got 0 on the other side. So when we do this, let's kind of go back up to our implicit differentiation technique here. Apply the derivative, we did that. Differentiate each term, we've done that. Now we want to move all terms containing y prime, we want to get them on the left side. And then anything that doesn't have a y prime, we're going to move to the other side of our equation. So in this case, we're going to keep the 2y times y prime where it is, and we're going to move that 2x to the other side. So we're going to subtract 2x from both sides. And when we do this, this gives us the equation 2y times y prime is equal to negative 2x. And then for our last step, we actually want to solve for just the y prime. So we want the y prime all by itself. So we got to get this 2y out of there. And the way to do that is just by dividing. And so when we do this, we end up with y prime is equal to negative 2x over 2y. And if we cancel off the 2's, we end up with negative x over y. So there's our formula for our derivative. So in this case, we could say that dy dx, or if we just want to keep calling it y prime, perfectly fine, is negative x over y. Okay. So now we can use that derivative just like we would regularly use a derivative. So we can use that to figure out the slope of our graph or the slope of our tangent line at a specific point. So for part 2, let's find the slope of our tangent line or the slope of our graph at this point 1 comma square root 3. So the only thing that's maybe a little bit different here is in this derivative, there's both x's and y's. And that's okay, because in our original equation, again, had both x's and y's in it. It wasn't in the form y equals. So when we do the derivative, we should kind of expect that there's going to be both x's and y's in it. And that's perfectly fine. So when we evaluate, we're going to need to know both the x and the y coordinate here, and we're going to plug them in. So let's see what we get. So our slope is going to be the derivative, and we're just going to evaluate x when x is equal to 1 and when y is equal to square root 3. So the x coordinate and then our y coordinate here. So we're going to evaluate this formula, negative x over y, when x is equal to 1 and when y is equal to square root 3. And again, this vertical line just means evaluate. So if we plug in, plugging 1 in for x, so we get negative 1. And then y is square root 3, so we end up with square root 3. And there we go. We got our slope. And this seems plausible. So if we go back, I think I had the graph in here somewhere. Yeah, here. So here's our point. We're at the x-coordinate 1, the y-coordinate's square root 3, so just a little bit under 2 there. And we found that the slope of our curve, the slope of our tangent line, was negative 1 over square root 3. It's negative, so our slope is, our tangent line is kind of pointing downward like this. All right. So we're going to try, we'll spice things up in some later examples. So in example 2, we'll do this one in class though. We're going to see what happens if we have a term that has both x's and y's in it. So there we're going to have to do, maybe some more of our advanced derivative rules, product, quotient, or chain. So we'll see that in class. Bye-bye.